Good day, math learners. This time, we will talk on the Fibonacci sequence. This kind of sequence is not considered as arithmetic nor geometry because the terms in the sequence don't have common difference nor common ratio. But this is a special kind of a sequence because of its unique ways on determining its terms that gave rise to other patterns. Do you know who discovered the Fibonacci sequence? It was named after the mathematician Leonardo Fibonacci of Pisa, or Leonardo Pisano Bugoglio, and Fibonacci was his nickname, which means son of Bonacci. In the year 1202, he was considered as the most talented mathematician of the Middle Ages, published his famous work, Liber Abaci. The original problem that Fibonacci investigated in the year 1202 was about how fast rabbits could breed in ideal circumstances. Fibonacci sequence is associated to a herd of rabbits started with one pair of adults, one male and one female. Each adult pair bears one pair of offspring, one male and one female monthly. Each pair of young rabbits become adults and bears its offspring at 2 months old. Assuming that there is no casualty, how many pairs of adult rabbits are in the herd at the end of n months? Fibonacci considers the growth of an idealized rabbit population with these assumptions. In the first month, there is just one newborn pair. Newborn pairs become fertile from their second month onwards. Each month, every fertile pair begets a new pair. The rabbits never die. The tree diagram below shows the growth of the colony for the first 6 months. Again, the rabbits are able to mate at the end of its second month. A pair of rabbits can produce another pair of rabbits and so on. And the number of pairs of rabbits in the field at the start of each month is 1, 1, 2, 3, 5, and 8. How many rabbit pairs are bred on the 7th month? How about on the 8th month? Can you see how the sequence is formed and how it continues? The Fibonacci sequence is associated the numbers of rabbit pairs every month form the sequence 1, 1, 2, 3, 5, 8, and so on. The pattern shows that each successive term is the sum of the preceding term. The Fibonacci sequence is defined by the recursive formula. F sub n is equal to f sub n minus 2 plus f sub n minus 1, where f sub 1 and f sub 2 is equal to 1. To illustrate the Fibonacci sequence, f sub 1 and f sub 2 are equal to 1. To get the third term of the Fibonacci sequence, get the sum of two preceding terms, which are f sub 1 and f sub 2, and their equivalent values are 1 and 1, and the result is 2. To get the fourth term of the Fibonacci sequence, get the sum of its two preceding terms, which are f sub 2 and f sub 3, and their equivalent values are 1 and 2, and the result is 3. To get the fifth term of the Fibonacci sequence, get the sum of its two preceding terms, which are f sub 3 and f sub 4, and their equivalent values are 2 and 3, and the result is 5. To get the sixth term of the Fibonacci sequence, get the sum of its two preceding terms, which are f sub 4 and f sub 5, and their equivalent values are 3 and 5, and the result is 8. Number 1. How many rabbit pairs are bred on the 7th month? How about on the 8th month? The solution: use the formula of the Fibonacci sequence, which is f sub n is equal to f sub n minus 2 plus f sub n minus 1. Substitute the value of n, which is 7 because we are looking for the 7th month. So f sub 7 is equal to f sub 7 minus 2 plus f sub 7 minus 1. And then simplify the formula and we come up f sub 7 is equal to f sub 5 plus f sub 6. Then substitute the values of the 5th and the 6th terms of the Fibonacci sequence, which are 5 and 8. And the 7th term is 13. Therefore, there are 13 rabbit pairs are bred on the 7th month. To get the 8th term of Fibonacci sequence, just use the same process in getting the 7th term. So since we are looking for the 8th term, substitute the value of n, which is 8, and it will become f sub 8 is equal to f sub 8 minus 2 plus f sub 8 minus 1. Simplify the formula and the equation becomes f sub 8 is equal to f sub 6 plus f sub 7. Substitute the values of the 6th and 7th terms of the Fibonacci sequence, which are 8 and 13. And the 8th term is 21. Therefore, there are 21 rabbit pairs are bred on the 8th month. Example number 2. Using the problem on rabbits population, how many pairs of rabbit will there be after a year? For f sub 1, it is equal to 1, and this is intended for the first month. F sub 2 is equal to 1, and this is intended for the second month. So since we are asked to get the pairs of rabbit after a year, so we look for the 12th term of the Fibonacci sequence. For f sub 3, or the 3rd term of the Fibonacci sequence, it is equal to 2. For the 4th term of the Fibonacci sequence, it is equal to 3. For the 5th term of the Fibonacci sequence, it is equal to 5. For the 6th term of the Fibonacci sequence, it is equal to 8. For the 7th term of the Fibonacci sequence, it is equal to 13. For the 8th term of the Fibonacci sequence, it is equal to 21. For the 9th term of the Fibonacci sequence, it is equal to 34. For the 10th term of the Fibonacci sequence, it is equal to 55. For the 11th term of the Fibonacci sequence, it is equal to 89. For the 12th term of the Fibonacci sequence, it is equal to 144. Thus, there will be 144 pairs of rabbits after a year. Number 3. Find the next 3 terms of the sequence 3, 7, 12, 18, and so on. The given sequence is not an arithmetic, not a geometry, nor a Fibonacci sequence. However, just like Fibonacci sequence, it has a unique way of identifying terms that still give rise to other patterns. Note that there is no common difference, but the difference increases by 1 for each term. For example, the difference of the second term, which is 7, and the first term, which is 3, is equal to 4. The difference of the third term, which is 12, and the second term, which is 7, is equal to 5. The difference of the fourth term, which is 18, and the third term, which is 12, is equal to 6. So as you can see in the pattern, we can get the next 3 terms of this sequence by increasing the difference to 1 for each term. So the difference of 5th term and the 4th term is equal to 7. To get the value of the 5th term, add the 4th term, which is 18, and the difference, which is 7. And the result is 25. the expected difference of 6th and 5th term is, okay, this is A. So add 25 and the difference 8. The result is 33. The expected difference of 7th and 6th term is, okay, 9. So add 33 and 9 to get 42 as our 7th term of the sequence. So the next 3 terms of the sequence 3, 7, 12, 18 are 25, 33, and 42. Number 4. Find the 7th term of the sequence 3, 6, 18, 72, and so on. Again, this is not an arithmetic, geometric, nor a Fibonacci sequence, but just like Fibonacci sequence, it has a unique way of identifying terms that still gave rise to other patterns. Let's observe. Consecutive terms here are multiplied respectively by consecutive integers. So, in other words, if you're going to get the ratio of the second term, which is 6, and the first term, which is 3, the result is 2. If you're going to get the ratio of the third term, which is 18, and the second term, which is 6, the result is 3. If you're going to get the result or the ratio, if you're going to get the ratio of 72 and 18, the result is 4. If you're going to get the ratio of 360 and 72, the result is 5. If you're going to get the ratio of 2160 and 360, the result is 6. Now, what must be the ratio of the 7th term and the 6th term? Okay, it is expected that it is 7. So to get the 7th term, we are going to multiply 2160 by 7, and the answer is 15,120 as our 7th term of the sequence. Thank you for listening, math learners. Have a nice day ahead.